Okay, we'll get going with this. Welcome, everybody. Happy Friday. Got a packed house. So we left off a little over halfway through chapter 9. We've got a good chunk of this material down. I left off with some anaerobes is kind of where we're at with this. And there's a couple of examples. Truly, there are lots of examples, and we can think even in our own bodies of some potentials where we can see some anaerobic bacteria, even in our mouths, providing a pretty good opportunity for some of these organisms to survive. So this image shows us a couple of potentials. This bog, down in the bog and the sediments, they become very anaerobic. There are potentials in the water for organisms to be thriving in oxygen rich kind of habitat. And then as we move down into the sediments, that oxygen gets kind of cut off. And as we go deeper down, it becomes truly more anaerobic. And there are some organisms that really thrive in those sorts of situations. When we think about early types of microbes, truly these anaerobic organisms were really the first players when we think about single-celled organisms. And then we see other potentials for changes, evolution within these different microbes where we start seeing oxygen being utilized. But initially, we think more of an anaerobic type of condition, all right? So still something that we can see. And in the gut of cows and others, but in the first bit of the cow, there's 4 stomachs in a cow. So in the first one, the rumen, this is a very anaerobic type of habitat, and there's a lot of bacteria that are helping to metabolize some of the cellulose that the cow is breaking down as it's chewing up its cud, its grass, or whatever else it's consumed, the hay. It helps to break that stuff down, breaking down the cellulose and releasing sugars that it can digest as it moves into other compartments. So there's some methanogens that in turn get releasing methane out of the back end of the cow. Huge contributors to some of that. And then other obligate anaerobic bacteria. And we'll go through here. I think it might be the very next slide, or a couple down the road, and show you some differences when we start thinking about aerotolerance. Can we handle it or not? And an obligate anaerobe cannot tolerate any oxygen, like down in the bog or in the gut of these cows, all right? Can't have it. I knew it was the next slide. So we got a couple of tubes up, a handful of tubes up here. These are a specialized type of media called thioglycolate that when prepared properly, they create an environment in these tubes that gives some gradation with the amount of oxygen that's available. And truly, it's a situation where we think about being able to cultivate anaerobic organisms in a lab, all right? There are some issues. Some anaerobic bacteria are very, very sensitive and can't handle being manipulated in the presence of oxygen at all right? The ones we will think about working with in the lab, they're a little bit more forgiving, and they can handle a brief period of exposure, like going from one tube onto the loop and out in the air and back into a new tube. They'll be okay. But there are numbers of anaerobic organisms that simply doing that, they would die on the loop, right? And in turn, trying to manipulate those things, we would be dealing with them not on the bench top, but in an anaerobic chamber. And I'll show you one of those in just a second, all right? But that would set the stage where you could be doing these manipulations without the fear of your organisms dying just as you're trying to transfer, all right? So thioglycolate tubes give us an opportunity to really kind of see what sort of potentials the microbes might have. And we're working with handfuls of different types of bacteria in the lab. We're going to look at some of these thioglycolate tubes and inoculate them with some different organisms and see how do they grow, all right? And you have all looked at some of the broths where we've seen some turbidity, right? A little bit of cloudiness in those broths. And in these thioglycolate tubes, the red dots are showing us, oh, here's where the bacteria is going to be. But really, when we look at those tubes, we'd see like a little band of turbidity, a cloudiness in there. Up at the top of the tube, with this first one in A, would be our obligate aerobes. These are the ones that want oxygen. They have to have it, all right? And they'll be right up at the surface of these tubes where it's available, all right? The obligate anaerobes are the complete opposite, all right? And they're going to be down at the bottom of the tube. You're not going to see any sort of growth except for clear down here at the bottom where there is basically no oxygen. This is like the bottom of the bog deep down in the sediment, all right? Then there's some variation as we move through here, all right? But this is the first two are the obligates. You flat out have to have oxygen or you can't live with it, all right? The others, there's some variability, right? We've got some potentials. Lots of organisms maybe growing in our gut. E. coli is a great example. It's one that we would say is a facultative anaerobe. These organisms have the opportunity to grow in varied environments, all right? In the lab, if we want them to grow really well, we inoculate them into a flask of media. It's got good nutrients in there. We put them in an incubator at 37 degrees Celsius, our temperature. That's what E. coli wants. And we shake those flasks. They're in a shaking incubator. So that shaking allows oxygen to kind of be churning around in those flasks, and it gives them ample amounts of air, and they can grow very well, like up here at the top, right? A good amount of oxygen, they grow super good, all right? And then we can look down toward the tail end of this tube, where oxygen gets very low. They can grow. They're not growing as well, but they can still grow, all right? So these facultative anaerobes have the potential to use cellular respiration to metabolize their sugars and other nutrients, but to metabolize these things and break them down. And they also have the potential to go through fermentation pathways where they're not utilizing oxygen and they're not producing boatloads of energy like you would with aerobic respiration. So the growth lower in the tube is slower because there's not as much oxygen and they're not able to metabolize as rapidly. So they can't grow quite as quickly, right? E. coli growing in our intestines doesn't grow like it grows in the lab where we're giving it copious amounts of oxygen. It grows pretty slowly, right? Because it's more of an anaerobic type of habitat down there, all right? So differences, all right? And this tube kind of looks almost like the whole thing's kind of turbid when you look at it, all right? Sort of a gradient, more turbidity toward the top, but the whole thing looks kind of turbid. The aerotolerant anaerobes, these are kind of just more evenly dispersed, all right? They can handle some oxygen, but technically they're not using oxygen as the final electron acceptor in cellular respiration like we see our facultative ones doing. So this one's more of the even dispersion, all right, as we see this kind of all throughout. And then the microaerophiles, these ones, they can't tolerate low levels of oxygen, but they also like a little bit of CO2, not full oxygen, but not really depleted as well. So they're not right up at the surface, but they're just the littlest bit below it, all right, giving us a perspective as what sorts of habitats some of these things could potentially maybe thrive in, if you will, all right? So a quick question. as we look at this figure, do you think there's anything wrong with this picture that, I mean, has kind of been left out of the mix? Any thoughts? So silent, I'll give you a hint. It has to do with the tubes. Any Zoomers have a clue for what's up? All of these tubes right here are just open. These are open open to the air. Thioglycolate tubes we don't want that to happen, all right? Every one of these, you guys all have worked with test tubes with broth or with the slants in there, and they've all been slip caps. The little caps that easily pop right off and go right back on. All they really are is just a kind of a dust cover. It doesn't provide an airtight seal. But when we work with thioglycolate broths, these things are in test tubes that have a screw cap, and it screws on there tight, all right? When they first get autoclaved, everything in there, the caps are loose. It gets cooked up, and as soon as it comes out of the autoclave, those lids are screwed on. While they are still cooking hot, they're screwed on. You've got gloves on, the UV glove. You've got your gloves on to screw those caps on, because just sitting there for a few minutes with the caps loose, oxygen will come in there as the tubes start to cool off. And then technically these thioglycolates, there's a couple of different varieties. Some of them have some oxygen indicators that give you a greenish sort of tint, and others, I think the one that we use is pink or red, all right? But we may have switched it up and it might be green ones now, but usually it's red stuff, all right? So you would expect to see these thioglycolate tubes to have the littlest tint of color up at the top, even if those lids are screwed on tight, because there's a little bit of oxygen, this airspace here, right? There's a little bit of oxygen that gets down in here, and that's great for these obligate aerobes or others as we look at it, right? But we don't want the whole thing to look pink, or then it tells us this whole tube's full of oxygen. And if you've got an obligate anaerobe, that sucker would never grow in that pink or green tinted tube, either way, telling you this thing's full of oxygen, all right? And technically, you can take those tubes that have been, the colors evolved in there, you can loosen the caps, put them into a boiling water bath, boil them for about 10 minutes or so, and then quickly screw them back down, and it will push the oxygen up out of there, and your tubes are back into business, all right? Just because it's changed colors doesn't mean it's ruined, all right? If we see them, you know, like I said, a bit of pink in there, it's okay. But if the whole thing has changed color before you use it, that's trouble, all right? And these, as we inoculate them, we screw the lids on tight as well. Oftentimes when we're doing other things, like maybe your sugar ferments that you'll work with soon, those things, the lids are the littlest bit loose, so you can get a little bit of gas to escape out of those tubes. But thioglycolates, you want it to be a nice airtight seal to ensure if you got some of these things, you'll actually be able to see it. So there are some other potentials, all right? This is an anaerobic jar. There's technically a couple of potentials for this. We've got some where we have like a big glass, kind of like a pickle jar, probably was a pickle jar. Big glass jar, like a gallon-sized jar that the Petri dishes will fit in. And we fill it all the way up, almost all the way up to the top. And right before the plate or two before it's clear to the top, we put a Petri dish with a little tea light candle, little candle in there. And we light the candle and we screw the lid down. And as the candle burns, it burns up most of the oxygen, and then the candle goes out. And we've created a semi-anaerobic environment. It's not flat out completely missing oxygen, but it's used most all of it up. And you get some organisms that are able to grow, all right? I'm pretty sure we've switched the lab up with that the littlest bit. And instead of using a candle, we found that another pretty cool technique to deal with this are the hand warmers, where you know, the little things that you crack and then they warm up and heat your hands up. That chemical reaction is basically eating oxygen, right? If it's in your pockets, it's not that big of a deal, right? Your hands are nice and warm, done deal. But if you put it in this jar and screw the lid down tight on it, as it's going through its chemical reaction, it heats up and eats all of the oxygen, and it creates a considerably more anaerobic environment than that little candle did. All right. So pretty cool. This other one is more of a true anaerobic chamber. All right. And we've got, you know, some gauges up here that we can see that we've sucked all the pressure out of. There are techniques that we use, not with all of these gauges, but you basically have a chemical reaction with some water added to a catalyst, a palladium catalyst, that once it comes in contact, it sucks all of the air out of there and creates a true anaerobic environment. And now this chamber really is trying to get our obligate anaerobes, right? And if you're one of these obligate aerobes, there's no chance you're going to survive in this, all right? There's no oxygen for you to do anything with, all right? So we can get all sorts of potentials with this, especially thinking about some that might be anaerobic or facultative. This chamber over here, this glove box, is an anaerobic box. And this was what I was talking about a second ago. If we were working with organisms that truly can't tolerate the hint of oxygen at all, we would manipulate them in one of these chambers, right? I had a friend that he was doing some environmental microbiology, working with anaerobic organisms, and they had a big hood. It wasn't a glove box like this. But all of their tubes where the bacteria was growing were in little stoppered and sealed up tubes with like little metal bands around them. And then you would inoculate stuff with a needle, poking it through there, like, you know, a medicine vial or whatever. And all of the tubes, you know, like the thioglycolates have the littlest bit of oxygen up in there. All of these tubes would get purged with nitrogen gas, pumping all of the oxygen up and out of there, and all you're left with is nitrogen. And then it's a completely oxygen-free environment, and everything is manipulated without any sort of potential for those cells to come in contact with oxygen. Pretty crazy, all right? So this box sets the stage where it's similar like this, where there's just no oxygen. Everything within here is a CO2 rich environment where it's all piped in there, and there is no oxygen. It's just full of carbon dioxide, right? Setting the stage for the potential to manipulate things a little more easily. Although I'm looking at those gloves thinking, would it be very easy to do your, you know, microbiology in those big, you know, kind of unruly gloves? Maybe, right? All right. I feel like it's pictures like this that YouTube's like, you know what? We're going to suspend this lecture, right? This is just too gross, right? For 9 o'clock in the morning, are you kidding me, right? All right. So as we look at this, still focusing on anaerobes, all right? This image is a patient that's got diabetes. There's all sorts of potential issues that can happen with these individuals, right? There's a lot of nerve damage that can happen, especially in your feet. Then there's problems where now you don't feel something, your foot gets wounded, and you don't know it because you don't feel it. We end up in a situation where those wounds don't heal up very well, and we get some pretty nasty looking infections, maybe gangrenous infections. And this Clostridium perfringens is the culprit for gas gangrene, right? And I've never truly had the opportunity, and I kind of think thankfully so, to deal with any of this stuff firsthand, or work with Clostridium perfringens. There's other Clostridia that we'll work with in the lab that doesn't smell so good. This one is, you know it. It smells terrible, all right? And I have had handfuls of students that are working as nurses, as they tell me some details about this. You know, as you're going into that patient's room, you know this sucker is going to be nasty, right? You can smell it right as you're going in, right? That's disturbing, and it makes me just kind of want to know, right? How does it truly smell, right? You sort of want to know, right? So with a very low oxygen, with this dead tissue, we've got more of an anaerobic situation, and the Clostridium thrives in that situation, and in turn can cause some serious issues. Oftentimes, maybe resulting in amputation. And there are problems with that because it may tend to just keep progressing. And you start off maybe losing a toe, and then the foot, and then up to the knee. And maybe that's the end of you, right? Truly kind of disturbing, all right? And speaking of toes, holy cow. All right, that looks like some nail fungus, right? That's probably how his foot got wounded in the first place. The other toenail scratched him. We'll leave it at that. Switching over, right? So have you guys done catalase tests yet? None of the biochemical stuff yet. We're getting close though. Okay, so catalase is a test that we will do with bacteria, with some bacteria. Technically could do it with lots of them, but there's a few that it's more informative with, if you will. So some bacteria, really kind of a lot of bacteria, may have an enzyme called catalase, and it gives them the opportunity to deal with substances like peroxide, which we might think of as being hazardous, maybe something that could kill some organisms when it comes in contact with it. But if they happen to have catalase, they take the peroxide, H2O2, and they basically chew it up, releasing oxygen gas as these bubbles and water, right? That's what they turn the peroxide into. We have all used some peroxide. You get a cut and you put some peroxide on it and you see some bubbles, all right? There's catalase activity within our blood. We can see bubbling, all right? We also potentially have a scratch that looks infected. It's getting all red. Maybe you put some peroxide on it and you see some bubbling, thinking that's good, and you're maybe, getting rid of those organisms. Really, those organisms that are catalase positive are just chewing it up and spitting it out. And those are the bubbles you're seeing, right? Not that it's not going to provide a little bit of help with cleansing that wound. As it gets in there and you've got this bubbling action, I see some of these organisms potentially getting flushed up and out of that wound. That might be a beneficial aspect of it, but seeing the bubbling doesn't truly mean that you're killing that infectious agent, all right? It just shows that that thing's capable of dealing with it, right? So there are a couple of things where catalase tests become more important, all right? There's lots of biochemical tests that we will think about, and different types of organisms doing different things. Lots of gram-negative bacteria. We wonder, can they ferment sugars? And we use these ferment broths where they will change colors and potentially show us if they produced gas. But then there's some others, like some of our gram-positives, gram-positive cocci specifically, all right? We may look at a gram stain of some of these bacteria and see gram-positive cocci. And then the question is it staph or is it strep? That might be a question. Those are two pretty common bacteria that we think about causing trouble in people, all right? It's also some stuff that we could think of as being normal flora as well. But from a gram stain, we could see gram-positive cocci. Maybe we can truly see that it's clustered, making us think staphylococcus, or chains like streptococcus. Maybe we're not 100% sure, all right? If we've got like a petri dish with this bacteria growing on it, you want solid media so you can get the bacteria, and you put it, a little bit of the bacteria, on a microscope slide, just like you're gonna get ready to gram stain it, all right? But instead of spreading this little guy out, you just put a little blob of him on the slide and a drop of peroxide goes on the top of it. And if that peroxide starts to bubble, and it happens immediately, all right? If that peroxide bubbles, you know that organism is catalase positive. And if it doesn't bubble, just looks like a drop of water on there, then it's catalase negative, all right? And in this case, the peroxide's actually doing something to this organism, right? It can't deal with it, right? It doesn't have that activity, right? So this would be hazardous to those cells, whereas these cells say, oh, I drink peroxide for breakfast, right? And there you go. The staphylococcus are catalase positive, and the streptococci are catalase negative. And it's a quick test that clues you in very quickly as far as whom we could be looking at, all right? If we decided to test this on others, like, you know, boatloads of different gram-negative bacteria, a whole good gamut of them are catalase positive. That's not a very informative test for them. But when we're looking at the gram-positive cocci, it truly is something that can clue us into what we're really dealing with, all right? And in the future, when it gets close to your unknowns, this will be a test that's performed, and you'll likely do it on, you know, all of the unknowns, but a few of you will have some positive cocci that it will actually be informative with, all right? If you're dealing with negative rods, you may still do the catalase test just to get the data, but it may not really be anything that is going to tell you one way or the other, all right? Keep that in the back of your mind. So there are other things, enzymes that some of these bacteria have or could have that can also clue us into some potentials with them, and maybe some ideas like being more pathogenic, more disease causing, all right? So both of these petri dishes that we're looking at here are blood agar plates. So it's got probably sheep red blood cells. That's a common additive for the blood agar plate. Sheep red cells in these plates, and when they start off, they look more like this, dark red, all right? And dependent upon your type of bacteria, you can have alpha hemolysis, our first image, which is a partial clearing. It can break them down a little bit, but it can't completely destroy those red blood cells, all right? So alpha hemolysis, faint clearing, all right? Beta hemolysis, this is a complete lysis, all right? Breaking it down, and those cells would be eating the juices of the red blood cells as they've lysed them all right? That's the idea. And an organism that's beta hemolytic, we think of it as definitely having greater potentials to cause disease, all right? Streptococcus pyogenes, our friend that gives us strep throat, when it gets cultivated, it gets streaked onto a blood agar plate, and it would look like the beta hemolytic image that we see right there. Nice clearing on that plate. Streptococcus pneumoniae, a cousin of pyogenes. Streptococcus pneumoniae is an alpha hemolytic organism, partial clearing, right? Pneumoniae would be gram-positive diplococci, and pyogenes, both gram-positives. Diplococci with the pneumoniae and big long chains with pyogenes, right? Plating them out would show us some details like this, if that's truly what's on there. I don't know, all right? There's another one that we don't show up here, and technically you wouldn't see unless we were looking at the colonies growing on the plate. You wouldn't see any alteration with the blood itself. It's just growing right on the surface. We call that gamma hemolysis. And gamma hemolysis is no hemolysis. It's not breaking it down at all. It just grows on the plate, right? There's other nutrients besides the blood that the bacteria can be growing on, all right? So those are the three types. Gamma is nothing, alpha is partial, and beta is the complete destruction of those red blood cells, all right? So these plates can clue us in pretty quickly as to some of the possibilities of what we're working with. There are others that can also show some hemolysis patterns, alpha or beta, besides the two I described. The Staph aureus, the catalase positive one, right? Staph aureus and strep pyogenes, both beta hemolytic, right? And staph on your skin, all fine and good, but you get a wound where it gets in there, and now all of a sudden it's got access to blood, and it's super happy, and it grows very rapidly, and in turn potentially can cause some serious infections in those circumstances. Same with pyogenes, all right? This image, I feel like they could have maybe gave us a better picture than this. So motility is something that we're potentially curious about with some organisms, all right? Really wondering, do we have flagella or not, all right? It's not telling us the arrangement of their flagella. It's just telling us that they've got them, all right? And we would be thinking about, you know, a rod-shaped or bacillus-shaped bacteria, whether it's positive or negative, all right? So the cocci, we don't think of them as having these potentials, all right? It's those, you know, bacillus-shaped ones that have flagella. So this tube, there's a couple of different types of media that we can use to see motility. It might be a gelatin or nutrient auger deep. There's another one called a Sims deep that tells us some other things. You'll use some Sims deep a little bit later. And you can potentially see motility in these tubes, right? Whatever type of media it might be. So it's solid media, it's not a broth. And instead of using an inoculating loop to swab stuff on there, we use a little metal rod. It's called an inoculating needle, all right? It's still got the handle just like the loop, but instead of the loop on there, it's just a straight rod, all right? You touch a little bit of your bacteria, and you take that loop and you poke it straight down and pull it straight out of that tube, and you basically inoculate it right down in there, right? If that bacteria is motile, when it grows, this positive one, you can kind of see it, and I will try to highlight it here. Maybe not with my mouse. With my pen, I bet I can. Right over here, you can see this, sort of see it, some cloudiness going down there. And it kind of looks like a cone as it comes down, with a really wide at the top and then down to the bottom, as it's spreading out, motile, all right? The other one, the needle stick is right within here, and this bit, it's just a straight down stab, and you can see growth right along the needle line, but not spreading out, all right? So non-motile. There are other potentials where maybe you don't get to see any of this spreading out down into the tube. You only see growth up at the top of that tube, right? Just a bit of growth right on the top. What type of bacteria would that be? Oh man, test question. And it'd have to be an obligate aerobe, right? It's gotta be. It's just only growing right on the top of the tube, not clear down at the bottom. It's not growing anywhere in here where it's all just media, right? There's very little oxygen, right? Little bit, but not enough for the obligate aerobe to say I could grow clear down here, right? It might just be right up at the top, right? Then that really kind of begs the question, is it motile or not, right? You can't tell it from that type of a procedure. That might require some staining, all right? We're not going to worry about that. So these give us some opportunities. With the Sims Deep, it's testing for a couple of different things, right? And some of the things that we look at is the utilization of sulfur, really cysteine in the media, and it produces hydrogen sulfide. So this tube would turn black if it's positive for that. And in that circumstance, you wouldn't be able to tell if the bacteria was motile because the whole tube turned black. So you couldn't see it. You'd have to do a different test, like a gelatin or nutrionography, not the Sims, to really see if it was motile, right? That's too much stuff. All right. So shifting away from a little of that to some different types of conditions, habitats. There are lots of opportunities when we think about stuff like food preservation, where we may think about microbes potentially setting the stage for this food to be preserved or to be produced, maybe not necessarily preserved. And then there are other opportunities where we think about altering the pH, typically making it acidic, that becomes very inhibitory. Lots of bacteria, not all of them, but lots of them prefer to be very close to neutral, all right? And if you get really acidic or really basic type of a solution, it's going to be super inhibitory for the bulk of these bacteria, right? For the bulk of microbes, really, but bacteria is kind of what we're thinking about right now, all right? So it really kind of depends on your circumstances, all right? There are some fermenters, some lactic acid bacteria that we can utilize for the production of things like yogurt, right? And yogurt, if you're eating plain yogurt, you can definitely kind of taste that sort of tanginess with the yogurt. It's the acid, the acidity that bacteria has created in the process of fermenting the lactose sugars to create the yogurt in the first place, right? Sauerkraut, another idea with that, with some bacteria normally on the cabbage in the first place, and you set a situation up where you get a bunch of cabbage that you're going to make your sauerkraut with, and you put it into like a big crock or something like that, and you allow it to sit. And the bacteria that's on the cabbage starts to go through some fermentation. And after a couple of weeks, it's converted that cabbage into a nice, soft, tasty, or disgusting dish, dependent upon who you are, right? Some people like it, and some people can't stand it, right? Really kind of depends, all right? Homemade sauerkraut, I think, is fantastic. Store-bought stuff's okay, but some homemade stuff's pretty good. You could throw some spices in there, and now we're talking kimchi, and that stuff is delicious, all right? But it's the same sort of an idea, some fermentation, all right? I skipped over the pickles. There's lots of different potentials when we think about pickling things, adding salts and vinegar to this to set the stage that becomes pretty inhibitory for bacteria to grow, all right? And then our last little bit over here, the pico de gallo, this also more acid rich, that creates a situation that keeps it pretty well free of microbes, at least for a little bit, So it's kind of a range with these guys when we think about where they may like to be surviving, all right? And again, it's kind of setting the stage for some of these potentials, thinking food preservation, all right? There's other opportunities like adding salts to things or dehydrating things as we think more osmotic pressures, not pH shifts, all right? So pH first, all right? There are acidophiles, acid lovers, all right? Maybe thriving around 3-ish pH, but capable of surviving a very acid rich condition, pH of 1, even less than that, all right? Some of the acid mine tailings, you get these big ponds that are super contaminated, super polluted, very, very low pHs. Microbes, some of these acidophiles can be thriving in those habitats. And we've got the opposite spectrum with the alkaphiles liking more of a basic type of condition, around 9-ish as a peak for that, but we can see it approaching 12 and then going the other way as well, going toward neutrality, where they can kind of tolerate it, but they'd rather it being more basic. Same with the acidophiles, getting closer to neutrality, but they're not as happy, right? They grow much better when it's more acidic. Like I said, lots of stuff is more in this green realm, right? The neutrophiles, those that would prefer being closer to neutrality, closer to around 7 is where they'd really like to be. Most of the pathogens that we think about causing issues with us fit right into that category. That's where they would like to be, all right? And things that we might think of as causing issues in our foodstuffs, same idea. So creating more of an acidic sort of habitat makes it pretty inhibitory for those that are in that green realm to survive, all right? As we drop it down, 4 or 5-ish, there's really kind of no chance that they can tolerate that type of a condition, all right? So they're a little more narrow with what they can utilize, all right? Truly kind of depends, all right? There were a couple of labs that were done over and over and over, and I really felt like, why, right? Things like the pH stuff, lots of the microbes that we work with in the lab, they're neutrophiles. There's a few that might be pushing the acidophile range, but most of them neutrophiles. And we had some labs set up where you would get a dozen, maybe not a dozen, maybe 9 or 10 of these differing pH tubes that you would inoculate a battery of bacteria into to just see how do they grow. And then you come back a week later and come to find out most of them didn't grow at all, except for near 7. You got a pH of 6, 7, and 8. Those 3 tubes you'd see growth in, and then the others, both ends of it, nothing, right? I feel like it's a lot easier to just show this, talk about it real quick, and be like, you can't tolerate it if you're in either of these extremities, right? And the stockroom, the people making all of the media, it was hundreds of tubes for the intro lab that's got 100 students in there. And if we're talking a dozen tubes per student, that's a boatload of tubes, right? And when I went in there and said, I think we're going to scrap this one. And there's another one with sugar, not sugars, with salts. Same idea. Salt kills, right? Lots of things, right? They looked at me and just said, thank you, right? So many test tubes that they didn't have to prepare and didn't have to kill and then wash once they were done with all of that stuff. They were happy, right? And in turn, you don't know it, but you're happy too, right? You are happy. All right, I think this is cool. When I was first reviewing this a couple of days back, as I was going through stuff, I was like, well, that's cool, but dang it, why not Salt Lake? 4 slides or 3 slides down the road, Salt Lake's on here. All right. So it's okay. I asked and it showed up. All right. This image from space is Lake Natron, Lake Salt, right? In Tanzania. Natrium is salt, right? So the pink that we're seeing in here is some alkalophiles, the basic, and halophiles, salt lovers, and potentially the two together, all right? And you can see this nice big pink lake from space. And I think that's pretty sweet. So I know Salt Lake's coming up. I want it right here. This image is deep down in the bottom of the ocean, these black smokers, these hydrothermal vents spewing out nutrient-rich plumes from this volcanic vent, probably full of things like hydrogen sulfide. This is a pretty extreme, very extreme type of habitat. Cooking hot temperatures, all right? And very high pressures, all right? As it's coming out of here, superheated, super high pressure. So we've got barophiles able to deal with high pressures, right? We've got thermophiles able to deal with over boiling temperatures, but the pressure's so great that it's not boiling here. You don't see that, but it is. You would not like it, all right? And here we've got some of the tube worms all surrounding this. There are microbes all over thriving in this nutrient-rich environment, and the tube worms are eating them, all right? Really awesome type of habitat. And you can see there's some stuff down here, making some measurements, doing a little science down here. And it kind of makes sense as I look at this, because how could you get these organisms, these bacteria, how could you get them from the bottom of the ocean where it's 700 degrees Fahrenheit as the water is spewing out of these vents, cooking hot, right? And the pressure so much, if we're, pushing almost a mile deep in the ocean, how would you expect to grab some of these microbes and bring them to the surface and expect that they're actually going to survive and grow in a laboratory situation? How could you cultivate them? Where would you grow them, right? Be pretty stinking hard, right? Maybe grow them in an autoclave, right? I don't know. I don't think you could, right? So a lot of this stuff truly done right here, right at the source, to truly examine and see what's going on, because trying to cultivate it, almost impossible, all right? There's a lot of organisms that we've got hints of them, but to actually grow them up in a laboratory situation right now, we don't have those potentials, right? I think that's kind of cool. So speaking temperatures, there's all sorts of potential ranges that microbes might say, I could do that. I'm okay, all right? And then you get to a point that it's either flat out too cold or too hot, right? And it's similar with us, right? There are things, we'd like to stay nice and toasty warm, but we really don't like it when it's negative 20 degrees outside, right? That's not so good. And I'm pretty sure most of us probably don't like it when it's 120 degrees outside. Luckily, we don't have those high temperatures here, at least yet, right? So hot or cold, maybe not so good, but nice and toasty warm, right? 37 degrees Celsius, happy, right? At least my body is. My body's not so happy when it's 37 degrees outside or 98 degrees, pushing almost 100. Not so nice, right? I'm not so happy about that, right? But I can tolerate it, right? So the mesophiles, I want to start with them because really who we want to think about in here for the bulk of stuff fall into this category. The disease-causing bacteria grow at our temperatures, all right? So other extremes, we don't really think of them, at least typically, don't really think of them as causing any sorts of issues as far as disease goes, all right? So mesophiles have an optimal right at our body temperature, 37, love it, all right? Little bit window either way. They can survive lower temperatures, 15-ish degrees Celsius, about 45 degrees Celsius as their maximal, all right? And as we go either way, very inhibitory, all right? Jumping over here to the sacrophiles, these are the cold lovers. They like cold temperatures. Freezing temperatures, it's okay, right? They'd like it to be a little bit warmer, right? But approaching zero, they're okay. And even below that, all right? They'd be okay, all right? Some organisms, maybe growing in, glacier ice as a potential freezing cold, all right? But able to persist, all right? There are some potentials as we see this littlest bit of overlap between these two. Some of these sacrophile organisms, there are some that we think of really more mesophilic. They'd rather be at our temperature, but they can approach at this crisscross. They can approach these colder regions, all right? And some of them, Staph aureus as an example, can survive at colder temperatures. Chilling in the fridge, it could survive. Holy cow, it's time to go. So I saw him pop in here. All right, I will stop with that. I'll stop with the sacrophiles, the heat lovers, thermophiles, and hyperthermophiles like super high temperatures. And we will pick up just the last little tidbit of this stuff on Monday. Have a good weekend, everybody.